Traditional neurology frequently evaluates severe neurodevelopmental disorders, like autism, as structural damage. In this view, behavioral dysfunction is the result of permanent hardware destruction or irreversible wiring errors that cannot be physically repaired. The framework of neuro-recovery engineering approaches the problem differently. Instead of a static collection of chemical balances, it models the brain as a dynamic network. The underlying hardware remains physically intact. However, a history of severe metabolic shocks forces the system to drop its damping ratio to survive the impact. The hardware becomes trapped in what engineers call a hysteresis latch, a high-gain defensive state where the logic gates are locked by the memory of previous physiological trauma. Chronic signal saturation is the primary driver of this dysfunction. The system is trapped in a calibratable state issue rather than a state of permanent hardware failure. To prove that the hardware is intact but operating in a saturated state, we have to look past subjective psychological assessments and examine the raw electrical data. For decades, the electroencephalogram, or EEG, has been utilized in standard medical diagnostics to monitor brainwaves. Viewed through an engineering lens, the EEG is a real-time oscilloscope trace of the human neurovascular bus. We can map the theoretical engineering predictions of the Neuro-Recovery framework directly against peer-reviewed EEG data, comparing typically developing systems to autistic systems. By analyzing the exact frequency distribution of the brain's electrical output, we can bypass behavioral symptoms and identify highly specific hardware failure modes: saturation, attenuation, and jitter. We can read these electrical signatures exactly like diagnostic trouble codes on a motherboard, giving us a precise schematic to debug the human processor. The baseline telemetry profile of a typically developing brain exhibits a balanced power distribution across all major frequencies. Central to this balance is a clear alpha rhythm, peaking between 8 and 13 Hz. This acts as the system's global clock, a timing pulse enabling high-speed synchronization between distant processing nodes. The engineering framework makes a specific prediction regarding the failure of node 2 in the autistic brain, the astrocytes. Astrocytes clear the neural bus. When they fail to vacuum excitatory glutamate from the synaptic gap, they leave the high bit stuck. Because this bit is never cleared, the circuit stays electrically hot, generating massive high-frequency electromagnetic interference, or EMI. This prediction matches the clinical evidence. Researchers like Rojas in 2008 documented that resting state EEGs in autistic children show elevated gamma band power, the high-frequency range between 30 and 100 Hz. What clinical psychology interprets as behavioral hyperactivity or an excitatory imbalance is literally high-frequency electrical static bleeding across the hardware bus. This creates a mechanical paradox. The autistic brain is simultaneously redlining in the high-frequency bands due to that static, while browning out in the low-frequency bands as its metabolic energy reserves enter lymph mode. This chart compares typical power spectral density against the U-shaped profile in autistic systems. High gamma power on the right proves signal saturation. Excessive delta waves on the left prove logic brownout. Between them, the alpha rhythm global clock is severely attenuated. When the global clock decouples, it destabilizes the vagus communication bus, the primary link between the body's metabolic state and the brain's processor. This creates vagus bus jitter, forcing the hardware into an asynchronous, high-latency state where complex operations stall. We can observe exactly how this baseline hardware state corrupts incoming real-time sensory data from the environment. In electrical engineering, this is known as voltage clipping. Because the brain's internal noise floor is already saturated at the maximum voltage ceiling, incoming environmental signals have zero voltage headroom to operate within. Event-related potential studies, which measure the brain's immediate electrical response to a stimulus, consistently track this failure. Autistic waveforms frequently present with delayed, flat-topped peaks. The signal hits the ceiling and abruptly clips. Nuanced environmental data, like human speech, loses its resolution, rendering it to the processor as painful, distorted square waves. The framework also predicts specific failures for the remaining hardware components: Node 1, the microglia, and Node 3, the neurons. Microglia are the brain's maintenance drones. When latched in an inflammatory attack state, they fail to prune redundant synaptic connections. This leaves a dense, localized rat's nest of chaotic wiring. Simultaneously, node 3 fails to maintain adequate dielectric insulation. The myelin sheaths wrapped around the extended neurowires become severely thinned. Look at this technical trace. Dense overlapping waves on the left visually confirm local hyperconnectivity. The rat's nest forces signals to crosstalk locally, but as high-speed data travels to distant modules, poor myelin insulation causes the signal to bleed out, creating severe long-range hypoconnectivity. The macro wiring architecture is physically present, but the lack of synaptic pruning and compromised myelin insulation causes massive signal bleed, shattering the processor's global coherence. The strict alignment between engineering theory and clinical EEG data leads to a singular conclusion. The physical hardware is intact, but the signal environment operating within it is deeply compromised. These EEG anomalies are not permanent traits. They are diagnostic trouble codes, and each code dictates a highly specific intervention to clear the bus. To resolve the high-frequency gamma static caused by node 2 vacuum failure, we apply the first module of the technical stack. This hardware logic tree translates the electrical fault into a biochemical patch. We lower the systemic gain and restore voltage headroom by deploying N-acetylcysteine as a metabolic coolant to clear the static, alongside inositol to act as a current limiter. To patch the attenuated alpha rhythm and stop the vagus bus jitter, we eliminate high-friction metabolic inputs like refined sugars and apply strong grounding agents like glycine and magnesium to stabilize the voltage rails. To resolve low global coherence, we re-insulate the wires. Increasing choline and DHA repairs the compromised myelin sheath, prepping the system for the microglia to finally resume synaptic pruning. True neuro-recovery requires a shift in objective. We stop trying to medicate the psychology of a meltdown, and we systematically patch the underlying hardware state that triggered it. By treating real-time telemetry as our guide, we bypass static, generalized dosing tables. Caregivers and clinicians can customize the patch to the exact hardware status of the individual. The ultimate mechanical goal is to break the system entirely free of the hysteresis latch. We move the hardware into an optimized state of homeostasis known as laminar flow. The extreme U-shape of the power profile flattens, the gamma static subsides, and incoming sensory waveforms regain their sharp, unclipped peaks. By systematically dropping the internal noise floor, the inherently intact logic of the human processor finally emerges from the static.